Previously, we have introduced the concept of a power series, and we have seen an example of a power series such as this one, acting like a function, that is, when x is equal to 1/2, for example, this power series was to converge to 2, which is exactly the same thing as 1 over 1 minus 1/2. And when x is equal to 0, this will converge to 1, because it's 1 plus a bunch of zeros, which is also the same as 1 over 1 minus 0. However, this is not always the case. So when x equals 2, for example, this power series becomes a series that doesn't converge. Thus, it cannot be equal to the value of this function. So what it means is that the power series behaves like that function, not for all values of x, but only for some values of x, and all the values of x can be described as the solution of this absolute value inequality, or using an interval notation, it can be described like this. And this is what we would call the interval of convergence, and this is the topic of this lesson. So let's define the interval of convergence. The interval of convergence of a power series is the set of all values of x for which the power series becomes a convergent regular series. So when you have a power series which looks like this, right? And I'm giving you an example of a power series centered at 0. But what happens when you set x to be equal to something else? So let's say x equals to 5. Then what's going to happen is that this power series will become nothing but a regular series. And if it converges, that means 5 is in the interval of convergence, and if it doesn't converge, then that means it's not in the interval of convergence. And the first significant observation here is that all such values actually form a continuous interval. So the set of values of x for which the power series becomes a convergent series is always an interval. It's never a discontinuous or disconnected set of numbers. So your intervals of convergence always look like this. So this is going to be your center, whatever your series is centered at. And there is a theorem which we're going to take for granted, but it says that the values which we would call the interval of convergence will form a continuous interval around the center. And the question is now, how do we find the interval of convergence for any given power series? And let's consider the following problem. Let's say we have some power series centered at C, and the goal is to find the interval of convergence. Now, we're going to use the ratio test, but remember, the ratio test works for regular series, and in order for us to use the ratio test, we're going to imagine that we have a regular series here, because that's what the power series becomes when x is replaced with some number. And according to the ratio test, the limit of the n plus 1th term divided by the nth term and all that inside the absolute value must be less than or must be less than 1 in order for us to say that the series converges. So if we want to find that all the values for which the series converges, this will be a great starting point. And let's plug in everything in. Let's simplify. X minus c to the power n and x minus c to the power n plus 1 have a lot in common, so we can reduce by everything. And now we can take the x minus c outside of the absolute value expression. But remember, the limit is in terms of n, and since x minus c doesn't have n, so it can also come outside of this entire limit. So if we assume that this entire limit is equal to L, so of course there will be some work done over here, but if we for a second assume that that limit is equal to L, then this whole expression can be rewritten as L times x minus c, and we know that by the ratio test this series converges whenever the limit that we set up is less than 1. And now I want us to recognize that what we have here is a very simple absolute value inequality, which we learned to solve in algebra. So let's hit the pause button here and let's go real quick to algebra and let's revise some of that material that we learned in algebra. So when we have an absolute value inequality in this form, for example, how do we solve it? Well, first, let's make it more interesting, I guess, or less interesting. It depends on how you look at it. But let's solve this inequality. The first step we do, we isolate the absolute value by dividing both sides by whatever the number in front of the absolute value. In this case, 5. So 15 divided by 5 is 3. And then we use some knowledge of this type of absolute value inequalities, and we rewrite this inequality as a two-sided compound inequality. And then we isolate x in the middle by adding 2 to all three sides of this inequality. And if we do so, we end up with the solution. So it's going to go from -1 to 5. And this process can be generalized when we have inequality like this. And we can turn it into two-sided compound inequality like this, and then we can add c to all three sides. Or we can even actually write it like this. And the answer will always be an interval, the left boundary of which is c minus r, the right boundary of which is c plus r, and the center, as you may guess, is c. So in this case, the interval is centered at 2. And that means that we can actually predict what the answer is just by looking and recognizing the pattern in this absolute value inequality. So, for example, if we have inequality like this, we identify the center as -1, and the radius of the interval is 2, and therefore we can immediately write the answer. So it's going to be the interval centered at -1, and we're going to be subtracting and adding 2 to -1. So -1 plus 2 is 1, and -1 minus 2 is -3. So the answer is from -3 to 1. Now if we have an inequality like this, for example, then the first step, we will isolate the absolute value, and then we would identify the center as 4 and the radius as 1/2, and then the interval will be centered around 4, and we're going to be adding 1/2, so it's going to be a 4.5, and we're going to be subtracting 1/2, which will take us to 3.5. So the answer will be from 3.5 to 4.5 using the interval notation. So with this in mind, let's go back to this problem and let's solve this inequality. We're going to unpause, so we're going to continue from here. So let's hit the play button here in our development, and we have the following inequality. And the first step we do, we isolate the absolute value, and we now identify the center as C and the radius as 1 over L. So the solution of this inequality is centered at C, and the interval is built around the center, and we add 1 over L to obtain the right boundary, and we subtract 1 over L to obtain the left boundary. And the answer then in interval notation can be written like this. So what does this mean? This means that when x is in this interval, the inequality will be satisfied. Therefore, ratio test says that the series converges. So by definition of the interval of convergence, we found all the values of x where the series converges. So therefore, this is our interval of convergence. Now, an important question that needs to be addressed, well, at least it's the good rough draft of the interval. But before we continue the conversation, let's answer this question. What happens when we find that limit and it's not a number, but a 0 or, let's say, infinity? Well, let's discuss this. Let me remind you what L is. L is this limit right here. So remember, we said we need to do some work to find it. And if you found it and you got 0, what does that mean? That means we have the following inequality. And 0 times anything is 0. And 0 is less than 1 always. And therefore x can be any value. And as an interval, what does it look like? That means the entire number line becomes the interval of convergence. So it's like your right boundary is plus infinity and your left boundary is negative infinity. So yeah, when we have this case, we say the center of the interval is C and the radius of the interval is infinity. On the other hand, when L is infinity, we're going to end up with the following outcome. And the only way infinity times something could be less than 1 is when that something is equal to 0. So this is the only solution of this inequality. And therefore x is equal to C. And then we have an interval, which is not an interval, but rather a single point. So we can still describe it as an interval by saying center is C, but the radius is 0. So this is the theory of how to find the intervals of convergence. So let's do an example. And as we do an example, we'll finish the development of the theory. So let's find the interval of convergence for the following series. And we always start by setting up the ratio test limit. So we're going to take the n plus 1th term and divided by the nth term, and we're going to simplify. And we're going to separate. And in order for us to continue, we have to figure out this limit. So let's hit the pause button here. And let's find L. So L is the limit as n goes to infinity of 3 to the negative n over 3 to the power of 1 minus n. Since everything is positive, we don't really need the absolute value, but to simplify this expression, we're going to use the properties of exponents. And what do we have here? Seems like the limit is just 1/3. Now that we know what L is, we can continue the solution. And we're going to replace 1/3 for L. And to find the interval of convergence, we have to set this whole thing to be less than 1. And after we multiply both sides of this inequality by 3, we get this inequality. And this is a simple inequality in which we recognize the pattern, and the center is 1, and the radius is 3. Again, this is my center, this is my radius, and we can draw the interval. So it's centered at 1, and the radius is 3, means it goes from 1 to 4 and to -2. So this is my interval, and using the interval notation, let's hold on to that for a second, but we know that this particular series converges for all the values between -2 and 4. However, what we don't know at the moment, so this is where we're at. We know that the series converges here. We know that the series diverges here and here. What we don't know is whether it converges or diverges at -2 and 4. Why is that so? Because when x is equal to -2 or 4, we get the entire limit equal to 1. And therefore the ratio test is inconclusive. So in that case, what we do is we manually check the behavior of the power series at these boundaries. Because the ratio test is inconclusive. And let's check. When x is equal to -2, our series remember, we used to have, this is our original power series, but when x is equal to -2, what happens? We replace x with -2, as we suggested. So Now we don't have x, now it's just a regular series. So we should be able to identify whether it converges or diverges. And if we do it carefully here, we would factor out -1. We would split this -3 to the power n as -1 to the power n times 3 to the power n, and we would recognize this as an alternating series test. Alternating series, to which we would be more than happy to apply the alternating series test. But in this case, it may not even be necessary, because the limit of the nth term is equal to 3, which is not 0, and therefore the conclusion that this series diverges by the divergence test. So the final conclusion is that at x equals -2, our series diverges. Now we have to do the same exact thing at the other boundary, which is 4. So right now we know at x -2 our series diverges. What's going on at 4? So now instead of -2 we're going to plug in 4. So instead of -2 we're going to have 4. Now 4 minus 1 is 3 to the power n, and we don't have alternating series here, and it makes things a little easier. But in this case it doesn't matter much, because it still diverges. For the same exact reason. So the conclusion is that at x equals 4 it also diverges, and therefore we complete this image here. And we write the answer. Since the series diverges at the boundaries, we don't include the boundaries in the answer. So what is the interval of convergence for this series? It's from -2 to 4, and we're going to use the parentheses, not the brackets, to indicate that the boundaries are not the part of the interval of convergence. All right, let's try another example. Here's our original series. It is centered at x minus 3. And the first thing I want to do here is I actually want to reindex it to make it so that the power of the general term is n, not n plus 1. So I'm going to subtract 1 from every appearance of n and add it to the sigma notation, but these two series are exactly the same. Now, to find the interval of convergence, we're going to use the ratio test. We're going to set up this limit. We're always going to do the ratio test, so the steps are pretty straightforward here. We're going to take the nth term and we're going to divide it into the n plus 1th term. And you can always count on the x minus c to the power n plus 1 divided by x minus c to the power n, reducing and just becoming the absolute value of x minus c, in this case x minus 3, outside of the limit, and that will allow you to just focus on the limit. So this particular limit, we have to reduce quite a bit here, so we're going to have 2 to the power n times n minus 1 factorial divided by 2 to the power n minus 1 times n factorial. And we don't need the absolute value here because everything is positive. But we do need to find this L. To find L, we're going to simplify the expression. So things cancel nicely there. I guess if I have to show all the work, it would be like this. This is gone, this is gone, and at the end we just have the limit of 2 over n as n goes to infinity, so the limit is equal to 0. So what do we have here? We have 0 times x minus 3, and we want that to be less than 0, but 0 is always less than 1, so we kind of go in this way of reasoning here, and since 0 is always less than 1, then my interval of convergence will look like this. It will be centered at 3, and it will be all the values of x. And we identify the center as 3, and we identify the radius as infinity, and the answer will be the interval of convergence is from negative infinity to infinity. All right, let's do another one. Let's find the interval of convergence of this power series. We're going to do this by setting up the ratio test. So we're going to take the n plus 1th term and divide it by the nth term. And like I said before, you can always count on this absolute value of x minus the center being taken out of the limit, and then focusing on finding this limit kind of makes it easier to organize your work. We don't need absolute value here because everything is positive, and if we call this L, L will be the limit as n goes to infinity, and n factorial times n plus 1 over n factorial. N factorial is gone, and we just have the limit of n plus 1 as n goes to infinity, which of course is equal to infinity. And when you have an equation or inequality, infinity times x minus 2 in absolute value, that must be less than 1. That means only one thing, that x minus 2 is equal to 0. And the answer then is not an interval, but rather a single point. However, we can still think of it as an interval centered at 2. It's just the radius is 0, and to write it in interval notation, I guess we can do something like this. It's the interval from 2 to 2, or we can just write it as a single point using the set notation. All right. So again, when L is 0 or infinity, the answer is pretty straightforward. So let's do one more problem where we get something interesting. So we're going to start by setting up the limit. For the ratio test, and we can take out this x minus 2 absolute value out of the limit, and inside of the limit we still have n over n plus 1. And here I'm just gonna speed up this process, but we don't need much effort to find this L, right? It's just equal to 1. So this whole expression just becomes absolute value of x minus 2, and per ratio test it must be less than 1. So the image that we're getting right now is this. We are centered at 2, the radius is 1, so we are going 1 to the left and 1 to the right, and we definitely know that in between the series converges and outside the series diverges. What we don't know yet is what's going on at 1 and 3, because the test is inconclusive at those points. So what we're going to do is we're going to manually check what the series does when x equals 1 and when x equals 3. So we're going to take the original series and we're going to replace x with 1. And we're going to replace it with 3. And what we see is when x is 1, we get an alternating harmonic series, which we know converges by the alternating series test. But when x is equal to 3, we get the actual harmonic series, which we know diverges because it's a p series, and p is equal to 1. So what we learn is that at 1 the series converges, so we're going to include 1 in the interval, and at 3 the series doesn't converge, so we're not going to include 3 in the interval. So that creates the interval of convergence like this. So the final answer for this problem is using the interval notation 1 in a bracket, 3 in a parenthesis. So this series converges for all values between 1 and 3, including 1, but not including 3. So we discussed the idea, the concept of the interval of convergence and how to find it for any given power series.